Welcome to the Deep Sleep Discoveries channel. There's nothing you need to do right now but settle in, let your breathing slow and allow yourself to drift into the quiet world of rain. For the next little while, we'll explore together the gentle mysteries of water falling from sky to earth, each fact a soft step deeper into rest. Rain has been falling since before there were eyes to see it, before there were ears to hear it, and tonight these small truths will carry you into sleep. Just before we begin, if you enjoy these sleepy science explorations, please consider liking this video and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. A large raindrop falls at approximately 20 miles per hour, while smaller drops drift down much more slowly, some at just 2 miles per hour. The size of the drop determines everything about its journey, the air around it pressing against its surface, slowing its descent into something almost leisurely. A tiny drop of drizzle takes its time, lingering in the atmosphere, while its larger cousins rush toward the earth with purpose. But none of them fall faster than the air will allow, each one reaching what scientists call terminal velocity, that perfect balance between gravity pulling down and air resistance pushing up, a dance of forces that happens without thought, without effort, in every rainstorm that has ever been. Raindrops are not teardrop-shaped. Small drops are perfect spheres, while larger ones flatten into hamburger bun shapes as they fall. Surface tension pulls tiny drops into flawless round beads, the same force that lets water striders walk on ponds, holding each molecule to its neighbor with invisible threads. But as drops grow beyond 2 millimeters, the air rushing past begins to push against their bottoms, flattening them into shapes that look more like soft buns or kidney beans floating through the sky. If they grow too large, beyond 6 millimeters, they cannot hold themselves together anymore and break apart into smaller drops, each one finding its own perfect size for the journey down, splitting and reforming in a process as old as weather itself. Rain is older than the dinosaurs. The same water has been cycling for 4 billion years. The drops falling tonight have fallen before, countless times, each one a traveler through deep time. They have been ocean and cloud, river and ice, snow on mountains that no longer exist, rain on forests that turned to coal. The water in a single storm may have fallen on the first simple bacteria, on trilobites in ancient seas, on ferns in the age of giant dragonflies. Every raindrop is ancient beyond imagining, and yet eternally renewed, the same molecules dancing through the same cycle, rising and falling, freezing and melting, forever moving through the systems of this planet in a rhythm that predates almost everything we think of as permanent. The smell of rain, called petrichor, comes primarily from geosmin, a compound released by soil bacteria when raindrops disturb the earth. These bacteria, called actinomycetes, live their quiet lives in the soil, breaking down organic matter, and when they die or when rain disturbs them, they release this molecule into the air. Humans can detect geosmin at concentrations as low as 5 parts per trillion. Our nose is extraordinarily sensitive to this particular scent, perhaps because for our ancestors the smell of rain meant water, meant life, meant survival. The word petrichor itself means stone essence, from the Greek petros and ichor, that fluid the ancients believed flowed in the veins of gods. And there's something sacred about it still, that earthen perfume that rises when the first drops hit dry ground. A single raindrop contains billions of water molecules. Each molecule is just 3 atoms, 2 hydrogen and 1 oxygen, bent at an angle of 104.5 degrees. But together they create something that can carve canyons, fill oceans, sustain forests. In one modest drop, the kind that leaves a small dark circle on pavement, there are approximately 1.5 sextillion molecules. A number so large it loses meaning, becomes pure vastness. Each molecule vibrates and spins, bonding temporarily to its neighbors through hydrogen bonds that form and break trillions of times per second, the whole drop held together by forces we can name but never quite see, a microscopic ballet of attraction and release, order and chaos, happening in something as simple as rain. Rain begins as ice crystals in clouds, even in summer storms. Up where the air grows thin and cold, water vapor finds those tiny particles of dust or salt and begins to freeze around them, building crystals of ice in temperatures far below what we feel on the ground below. These crystals grow as more vapor deposits directly onto them, bypassing the liquid state entirely, creating structures of frozen geometry. Only as they fall into warmer air do they melt, transforming from solid to liquid somewhere in their descent, so that what reaches your skin as summer rain began its life as ice, as winter up high where the air is always cold. Even on the hottest day, rain remembers frozen beginnings, carries that history of ice down through the warming layers of atmosphere. The average raindrop is about 2 to 3 millimeters in diameter. Hold your fingers close together, just 1/10 of an inch apart, and you're seeing the size of a typical raindrop, though they range from the barely visible drizzle to the fat drops that splash dramatically on windshields. This size isn't arbitrary, but represents a balance, drops small enough to stay cohesive but large enough to fall without evaporating, the sweet spot of stability in an unstable journey. Meteorologists measure rain by counting and sizing these drops, understanding that a storm's character shows itself in whether drops are many and small or fewer and large, each pattern telling a story about the clouds above, the moisture content, the atmospheric conditions that birthed this particular rainfall. Size matters, in rain as in so much else. Raindrops smaller than 0.5 millimeters never reach the ground. They evaporate mid-fall. These tiny drops, barely more than mist, begin their descent, but the air around them is often too dry, too warm, and they simply vanish before completing their journey, returning to vapor before they can wet the earth. It's a quiet disappearance, each microscopic drop giving itself back to the atmosphere in a transaction we never witness, happening in the space between cloud and ground, the in-between realm where water changes state as casually as we change our minds. These drops that never land are still part of the cycle, still matter, their evaporation cooling the air slightly, adding humidity, affecting everything around them even in their failure to reach conclusion. Not every raindrop's story ends with Earth. The sound of rain is actually thousands of tiny impacts creating a symphony. Each drop strikes a different surface, leaf, roof, soil, stone, and each surface responds with its own pitch and tone, the metal roof ringing higher than the wooden fence, the sidewalk's sharp tap different from the soft absorption of grass. Together, these individual strikes blend into what we hear as rainfall, a chord made of infinite notes, a texture rather than a melody. The sound varies with the size of drops and the surfaces they find. Heavy rain on a tin roof are different music entirely than drizzle on a forest canopy. We respond to this sound at a level deeper than conscious hearing, our nervous systems calming, our breathing slowing to match its rhythm, some ancient part of us remembering shelter, safety, water without threat. Rain can fall from clouds as high as 10 miles above Earth. At that altitude, the air is thin and brutally cold, temperatures dropping to -60 degrees Fahrenheit or colder, a hostile environment where water exists only as ice. The clouds up there are massive towers of frozen vapor, and the drops that form within them have a long way to travel, falling through different layers of atmosphere, each with its own temperature, its own humidity, its own winds. A drop falling from that height takes minutes to reach the ground, plenty of time to freeze, melt, collide with other drops, break apart, reform, experiencing more in its brief life than we might imagine possible. Looking up at rain, we're seeing the end of a journey that began miles overhead in clouds touching the edge of space. Each raindrop takes about 2 to 4 minutes to fall from a typical rain cloud. It's a longer journey than you might think, longer than it takes to boil an egg, to make a phone call, to walk 2 blocks. The drop doesn't rush, can't rush, falls only as fast as physics allows, moving through layers of air that push back against it, suspended for these minutes between sky and earth. In that time, the drop experiences temperature changes, air pressure shifts, collisions with other drops, everything that can happen to something falling through atmosphere. If you could follow a single drop from cloud to ground, you'd see a small odyssey, a tiny traveler making its way down through a vertical landscape we rarely consider, taking its time about the business of returning moisture from sky to soil. The moisture in a single rain cloud could fill millions of swimming pools. Clouds look insubstantial, just wisps of vapor, but they carry astonishing amounts of water. A typical cumulus cloud, the puffy kind that floats across summer skies, might hold 550 tons of water, all of it suspended in billions of tiny droplets too small to fall. Larger storm clouds can hold thousands of times more, moving water masses measured in megatons through the sky as casually as you might carry a glass across a room. All that water stays airborne through a combination of updrafts and the fact that the individual droplets are so small, their surface area so large relative to their weight, that air resistance keeps them floating. It's only when they combine into drops heavy enough to overcome that resistance that rain begins, the cloud slowly emptying itself, giving back what it carried. Raindrops collide and merge as they fall, growing larger. The journey down is crowded, millions of drops falling through the same column of air, and they bump into each other constantly, larger drops catching up to slower, smaller ones, different fall lines intersecting. When they touch, surface tension pulls them together into a single, larger drop, a liquid merging that happens without friction or resistance. This process, called coalescence, is one of the primary ways rain forms in warm clouds, drops colliding and combining until they're heavy enough that nothing can keep them airborne. It's a process of accumulation, many small things becoming fewer larger things, droplets that began separately finding each other in the fall and deciding in their mindless way to travel the rest of the journey as one. The air inside a raindrop is cleaner than the air around it. As drops fall, they sweep particles from the atmosphere, collecting dust, pollen, pollutants, trapping them in the water. But the interior of the drop, the heart of it, remains relatively pure, especially if the drop formed high in the atmosphere where the air is thinner and cleaner. There's something about this that feels like metaphor, the idea that inside even a raindrop falling through polluted air, there's a core of clarity, a center that remains untouched. Of course, by the time the drop reaches the ground, it has collected its share of the atmosphere's contents, carrying them down in solution, cleaning the air through its own contamination. Rain washes the sky by taking on its impurities, a process of transfer, purification through sacrifice. Rain forms around tiny particles of dust, salt, or smoke, so every raindrop carries a microscopic piece of the world at its center. These condensation nuclei, as they're called, are essential. Without them, water vapor might never condense into droplets at all, might remain as supersaturated vapor indefinitely. The particles can be sea salt blown up from ocean waves, dust from deserts carried aloft by wind, smoke from wildfires or factories, even bacteria or fragments of plants. Whatever it is, it sits at the heart of the drop like a seed, like the grain of sand that might become a pearl, and in a way, every raindrop is a pearl, a small world wrapped around a tiny piece of another world, earth and sky combined into a single falling entity. Nothing in nature happens in isolation, and rain is no exception. 90% of Earth's water that evaporates comes from the ocean. The seas are the engine of the water cycle, the massive source that feeds clouds, rivers, rain, everything. The sun beats down on those vast surfaces and water rises invisibly into the air, molecules breaking free from the liquid state and drifting upward, carrying heat with them. This ocean-sourced vapor travels on winds, sometimes thousands of miles inland, before condensing and falling as rain that may never see the sea again for years, for decades, locked in ice or aquifers or the bodies of living things. But it began in the ocean and will likely return there eventually, the sea calling back what it released, the great reservoir of the planet, both giving and receiving in cycles measured in weeks or millennia, patient as tides, vast as storms. A water molecule spends an average of 10 days in the atmosphere before falling as rain. 10 days of floating as vapor, invisible and free, rising on warm air, traveling on winds, moving from place to place in the sky before finally condensing around some particle and beginning the journey back down. In those 10 days, a molecule might cross a continent, might rise to the top of a towering thunderhead and fall back down inside the cloud multiple times before finally escaping as rain. It's a brief residence in the sky compared to the time water spends in oceans or glaciers, but it's the active phase, the time of movement and transport, when water does the work of redistributing itself across the planet. 10 days between rising and falling, between Earth and Earth, with sky as the temporary home. Plants release water vapor through transpiration that becomes 10% of all rain. Every leaf is a kind of pump, drawing water up from roots and releasing it through tiny pores called stomata, breathing out moisture as surely as we breathe out carbon dioxide. This transpired water rises into the air and becomes part of the atmospheric moisture that will eventually condense and fall. In forests, especially tropical rainforests, this creates a cycle where trees make their own rain, the forest generating the very precipitation it needs to survive, a closed loop of giving and receiving. The trees exhale and the sky inhales, and later the sky gives back what the trees provided, rain falling on leaves that will transpire it again, the water cycling through forest and cloud in a partnership older than most species now alive. One large tree can release 100 gallons of water into the air per day. 100 gallons, enough to fill a small bathtub, rising invisibly from a single tree in the course of one day's photosynthesis and transpiration. The tree pulls water from the soil, draws it up through its xylem against gravity, and then releases it from leaves high in the canopy, a process that both cools the tree and feeds the atmosphere with moisture. Multiply one tree by the millions in a forest and you begin to understand how vegetation drives weather, how forests create humidity, coolness, the very conditions that support more forest. Each tree a small fountain, each forest a source of rain, the land not just receiving water from the sky but actively participating in creating the conditions that make rain possible. The water cycle moves 12,900 cubic miles of water through the atmosphere annually. It's an almost incomprehensible amount, a volume that would fill a cube over 23 miles on each side, all of it evaporating, condensing, and precipitating in the endless exchange between earth and sky. This movement happens without fanfare, without machinery, powered only by the sun's energy and the physical properties of water, but it's the fundamental circulation that makes weather possible, that distributes fresh water across continents, that moderate climates and sustains every ecosystem. 12,900 cubic miles flowing invisibly through the air above our heads, falling as rain and snow, soaking into soil or running to the sea, then rising again to start the cycle over, the planet's circulatory system pumping life-giving water to where it's needed. Rain that falls on mountains can take decades to flow back to the ocean. It soaks into the ground and percolates slowly through layers of soil and rock, filtering downward into aquifers, emerging eventually as springs that feed streams that feed rivers, each stage taking time, sometimes years, sometimes decades. Mountain rain might sit in an underground reservoir for 20 years before seeing daylight again, and then spend another few years traveling down watercourses to the sea. This slow journey means that rain is not just falling in the present moment, but creating future water supplies, banking moisture in the earth for years to come. The rain of one decade becomes the spring water of another, time and water both flowing but at such different speeds that the connection between them becomes invisible, becomes memory stored in stone and soil. Groundwater from ancient rain can be thousands of years old. Deep aquifers hold water that fell in different climate regimes during ice ages or pluvial periods when the world was wetter, when now arid regions were green and well watered. This fossil water, as it's sometimes called, has been trapped underground since before recorded history, isolated from the modern water cycle, aging in darkness like wine in a cellar. When we pump such water to the surface, we're essentially mining history, bringing up rain that fell when mammoths walked the earth, when human civilization was just beginning. It's a non-renewable resource on human timescales, rain from another age, and once it's used, it won't be replaced for thousands of years, if ever. A reminder that not all water participates equally in the cycle we think of as continuous. The Amazon rainforest creates about 50% of its own rainfall. The trees transpire such enormous quantities of moisture that clouds form from the vapor they release, and these clouds rain back onto the forest, creating a partially closed system where the forest generates the rain it needs to be a rainforest. This means that deforestation doesn't just remove trees but reduces rainfall, because fewer trees means less transpiration, means fewer clouds, means less rain, means even fewer trees can survive, a cascade of loss spiraling downward. The forest and the rain are partners, each creating conditions that allow the other to exist, a relationship so tight that destroying one inevitably damages the other. It's a vivid example of how ecosystems create their own weather, how life and climate are inseparable, woven together in ways that can unravel faster than they can mend. Rain over the ocean has slightly different chemistry than rain over land. Ocean rain forms from water vapor that carries tiny amounts of sea salt, making it slightly more saline, slightly more conductive, chemically distinct in subtle ways. Land rain carries what the continental air provides: dust, pollen, particles of soil, sometimes pollutants from human activity, giving it a different chemical signature. This difference is small but measurable, each type of rain reflecting its origin, carrying traces of the surface over which its vapor rose. The rain that falls on you near the coast might taste faintly different than rain falling 100 miles inland, though the difference is too subtle for most people to detect. But instruments can tell them apart, can identify ocean rain from land rain by what it carries in solution. Another reminder that rain is not a uniform substance, but a variable one, taking on characteristics from the places it touches. A single water molecule may cycle through the atmosphere 5 to 6 times before returning to the ocean. It rises as vapor, falls as rain onto land, evaporates again from a lake, falls again onto a forest, transpires from a tree, falls once more onto a field, each time taking a different path, covering different ground, participating in different local cycles before finally making its way to a river and back to the sea. This multiple cycling means that rain is often already a veteran of the water cycle by the time it falls on you, a molecule that has been rain before, that has lived briefly in plants or animals, that has frozen and melted, that carries within its simple structure an invisible history of transformations. The return to the ocean is not immediate, but works through these iterations, the water taking the scenic route, experiencing the world in all its variety before going home. Virga is rain that evaporates before touching the ground, creating ghostly curtains. You see it as dark streaks hanging from clouds, precipitation falling but never arriving, dissolving in mid-air as it enters drier layers of atmosphere. It's beautiful and melancholy, the promise of rain that never fulfills itself, water that almost makes it but not quite, disappearing back into invisibility before completing its purpose. Virga is common in arid regions where the air near the ground is especially dry, eager to reclaim any moisture it can. Seeing Virga is watching the water cycle in its incomplete phase, the failed rain, though even this failure serves a purpose, as the evaporating drops cool and moisten the air through which they fall, changing the atmosphere even in their disappearance, preparing conditions that might eventually allow rain to reach the ground. Diamond dust is frozen rain that sparkles in Arctic sunlight. It's made of tiny ice crystals forming directly in clear, cold air, usually when temperatures drop below -30 degrees Fahrenheit. The crystals drift down slowly, catching light and throwing it back in bright flashes, creating the illusion of diamonds falling from a cloudless sky. Unlike normal rain or snow, diamond dust forms without clouds, just direct deposition of water vapor onto ice nuclei in air so cold that the vapor bypasses the liquid state entirely. It's a rare phenomenon, seen mainly in polar regions during the darkest, coldest months, when the air itself seems to crystallize. Walking through diamond dust is like moving through a soft glitter, soundless and strange. Each crystal a tiny prism turning the horizontal light of Arctic dawns into something magic, something that seems less like weather and more like the atmosphere dreaming. Freezing rain is liquid until it touches a surface, then instantly freezes. The drops fall through warm air and remain liquid, supercooled below 32 degrees Fahrenheit, but not frozen because there's nothing to trigger crystallization. Then they hit something, a tree branch, a power line, the ground, and in that instant of contact they freeze solid, coating everything in clear ice. The transformation happens too fast to see, liquid to solid in a fraction of a second, building up layers of ice with each additional drop. Freezing rain is one of winter's most dangerous phenomena, the weight of ice snapping branches and bringing down power lines, but it's also beautiful in a hazardous way, encasing the world in glass, every twig and leaf outlined in crystal clarity. The landscape transformed into something brittle and bright, heavy with frozen rain that was liquid just a moment before touching the surface that became its doom. Drizzle consists of drops smaller than 0.5 millimeters in diameter. These tiny drops barely seem to fall, drifting more than dropping, taking long minutes to descend through still air, light enough that a breeze can almost hold them suspended. Drizzle doesn't splash when it lands, but disappears into surfaces almost silently, accumulating slowly, wetting things gradually rather than soaking them suddenly. It comes from low stratus clouds, the grey blankets that sometimes settle over landscapes for days, releasing moisture in this tentative way, as if reluctant to commit to actual rain. Drizzle feels different on your face than rain does, more like mist than distinct drops, a wetness that arrives incrementally by degrees, giving you time to notice each stage of becoming damp. It's the water cycle at its most hesitant, precipitation that takes its time about everything, hurrying for no one. Convective rain comes from summer thunderstorms and falls in intense bursts. These storms build when the ground heats up and sends columns of moist air rushing upward into towering cumulonimbus clouds. The air inside these clouds churning violently, updrafts and downdrafts fighting for dominance. When the rain finally comes, it comes suddenly and heavily, drops large and fast, the whole intensity of the storm pouring out in minutes or hours rather than days. Convective rain can drop inches in an hour, flooding streets and overwhelming drainage systems, water coming down faster than the earth can absorb it. But it's usually localized, one neighborhood getting drenched while another a mile away stays dry, the rain following the terrain of heat and moisture that triggered the storm's formation. This is rain as event, as drama, the opposite of the gentle persistence of drizzle, water falling with urgency and force. Frontal rain happens when warm and cold air masses meet, creating steady precipitation. The warm air, being lighter, rides up over the cold air in a gradual ramp that can extend for hundreds of miles, and as it rises, it cools, and as it cools, its moisture condenses into clouds and then into rain. This rain is typically less intense than convective rain, but lasts longer, sometimes for days as the front slowly passes, bringing steady, widespread precipitation. Frontal rain lacks the drama of thunderstorms but has its own character, that persistent grey drizzle or moderate rain that seems like it might never stop. The kind of rain that soaks into everything, that settles into your bones and your plans, that makes you forget what sunshine felt like. It's the rain of transitions, the atmosphere rearranging itself, warm and cold negotiating boundaries, and rain is the byproduct of that negotiation. Water squeezed out of air as it's forced to climb and cool. Orographic rain forms when moist air rises over mountains. The air must go up to get over the peaks, and as it rises, it expands and cools, and its moisture condenses into clouds that cling to the mountainside, releasing rain on the windward slopes. This is why mountains often have lush green western sides and dry eastern rain shadows. All the moisture gets wrung out on the way up, leaving little for the far side. Orographic rain is reliable, predictable, happening whenever moist air blows in from the ocean or a large water body and encounters high ground. Some of the wettest places on Earth owe their rainfall to this mechanism, mountain ranges positioned where they can intercept moisture-laden winds and convert that moisture into prodigious amounts of rain, year after year, the geography itself creating weather patterns that can last for geological epochs. Acid rain has a pH below 5.6 caused by atmospheric pollutants. Normal rain is slightly acidic anyway, around pH 5.6 because it absorbs carbon dioxide from the air and forms weak carbonic acid. But acid rain is more acidic than this, its pH lowered by sulfur dioxide and nitrogen oxides from burning fossil fuels, industrial processes, vehicle emissions. These pollutants dissolve in rainwater to form sulfuric and nitric acids, and when this more acidic rain falls, it damages forests, acidifies lakes and streams, corrodes buildings and monuments, harms fish and other aquatic life. Acid rain was a major environmental problem in the late 20th century and led to clean air regulations that have significantly reduced it in many regions, though it remains an issue where industrial emissions go unregulated. It's a reminder that rain, for all its purity, carries what we put into the air, brings our pollution back down to earth, holds us accountable. Colored rain can occur when raindrops collect dust particles, yellow, red, or even black. Saharan dust blown across the Mediterranean creates red or orange rain when it mixes with storm systems, giving the rain a rusty tint and leaving a fine layer of desert on everything it touches. Volcanic ash can create black rain, drops so laden with particles that they're opaque, dark as ink. Pollen-heavy air in spring can create yellow rain, each drop carrying a payload of plant genetics, staining cars and sidewalks. These coloured rains are rare but dramatic, a visible sign of how far materials can travel in the atmosphere, how rain brings down not just water but whatever else is floating up there. The colour tells a story, where the air has been, what it's passed through, what the land or sea or volcanism has contributed to the atmosphere before this rain fell. Phantom rain is when you smell rain but only a few drops fall. You catch that petrichor scent, that earthy promise of moisture, and maybe you feel a drop or two, but the rain never really comes, the storm passing by or dissipating before it can truly rain. It's a tease, an unfulfilled forecast, weather that almost was but wasn't quite. Phantom rain happens when conditions are almost right but not quite sufficient. Maybe the air is almost humid enough, maybe the drops are almost large enough, maybe the storm is almost organized enough. The smell comes from those few drops that do fall, or from moisture in the air disturbing the soil, releasing that geosmin even without substantial rain. It's disappointment if you were hoping for rain, relief if you weren't, and always a reminder that weather is probability and not certainty, conditions that may or may not resolve into the rain they seem to promise. Mawsynram, India receives 467 inches of rain annually, the wettest place on Earth. That's almost 39 feet of rain each year, falling mostly during the monsoon season when moisture-laden winds from the Bay of Bengal hit the Khasi Hills and are forced upward, releasing their moisture in torrential downpours. During the wettest months, Mawsynram can receive 60 inches of rain in a single month, days of continuous deluge that makes going outside a challenge and turns the landscape into a cascade of waterfalls. The village has adapted. People wear full-body nup, woven bamboo shields that cover them like shells, and buildings are designed to shed water and resist the constant damp. Living in the wettest place on Earth means living with rain as the dominant fact of existence. Everything else organized around the reality of perpetual moisture, the sky a reservoir that empties itself over the same spot year after year with faithful intensity. The Atacama Desert in Chile went 400 years without rain in some areas. 4 centuries of dry skies, generations of aridity, a place so starved of rain that it's used to test Mars rovers because its soil chemistry is similar to Martian soil, both places where water is nearly absent. When rain does finally come to the Atacama, it can be catastrophic. The ground is so unused to water that it doesn't absorb well, and flash floods result from even modest rainfall. Some areas of the Atacama are so dry that there's almost no life at all, even bacteria struggling in that absolute desiccation. The lack of rain has preserved artifacts and mummies for thousands of years, the air too dry for decay. The Atacama reminds us that rain is not universal, that there are places on this planet where water has nearly forgotten to fall, where the water cycle has a hole, a gap, a region it mostly skips. Lloro, Colombia experiences rain about 280 days per year. That's rain roughly 3 days out of every 4, a place where dry days are the exception and rain is the default state of weather. Lloro sits in a region where the topography and winds create nearly constant precipitation. Rain falling gently most days, sometimes heavier but almost always present in some form. Living there means living with rain as a companion, planning around it but not being surprised by it, carrying umbrellas habitually, building houses with steep roofs and good drainage. The vegetation is lush, every surface covered in moss and ferns, the sound of dripping water a constant background. For people in Lloro, a dry spell of even 3 or 4 days is notable weather, the absence of rain more remarkable than its presence. It's hard for people from drier climates to imagine, but there are places where rain is as reliable as sunrise, where the question is not whether it will rain, but when. Antarctica is technically a desert, receiving less than 2 inches of precipitation annually. It's surrounded by ocean, covered in ice miles thick, but it's one of the driest places on Earth because the air is so cold it can hold almost no moisture. What precipitation does fall comes as snow, and it accumulates over millennia rather than melting, building the ice sheets that define the continent. The interior of Antarctica is extraordinarily dry, some valleys receiving almost no precipitation at all, cold, dry winds keeping moisture away, creating a frozen desert as hostile to life as any hot sand wasteland. The ice looks like abundant water, but it's ancient precipitation. snow that fell centuries or millennia ago and never melted, compressed into ice by the weight of snow falling on top of it year after year, building landscapes from frozen rain so old it predates human civilization. The wettest spot in the USA is Mount Wailea, Hawaii, with 373 inches yearly. The mountain sits in the path of trade winds that carry moisture from the Pacific, and its shape forces that moist air upward where it cools and releases rain almost constantly. The summit is one of the wettest spots on the planet, nearly always shrouded in clouds and mist, vegetation clinging to the wet rocks, the whole mountain a monument to orographic precipitation. Lower elevations can be relatively dry, while the summit drowns, all the rain concentrated at the height where the lifting air reaches its dew point. People rarely visit the summit. It's difficult to access and offers little visibility through the constant clouds, but the rain keeps falling whether anyone's there to see it or not, one of those reliable processes of nature, geography and meteorology combining to create conditions where rain is eternal. Cherrapunji, India once received 86 feet of rain in 1 year. That's the height of an 8-story building, all of it falling as rain on one location in 12 months, an almost incomprehensible deluge. This happened in 1860 to 1861, a year of extraordinary monsoon activity when the weather patterns aligned to dump unprecedented amounts of water on this hill station in the Khasi Hills. Cherrapunji and nearby Mawsynram trade places as the wettest locations on Earth depending on the year, both benefiting or suffering depending on your perspective, from geography that channels monsoon moisture directly onto their hillsides. The rain is so intense and regular that it has carved the landscape into dramatic forms, steep valleys and waterfalls, eroded slopes where only the hardiest vegetation survives. 86 feet in 1 year stands as a record that may never be broken. A year when the sky couldn't seem to stop opening, couldn't hold on to moisture, just poured and poured and poured. Some parts of the Sahara go a decade without rain. 10 years of blue skies, of heat without the relief of clouds, of air so dry it cracks lips and draws moisture from skin. When rain does come, if it comes, it's usually brief and localized, a shower that wets a few square miles and evaporates almost before it can soak in, leaving the sand darker for an hour before that too dries. The plants and animals that survive in such places have extraordinary adaptations, seeds that can wait decades for the one good rain that will let them sprout, bloom, reproduce, and die all in a few weeks before the drought returns. For people, rain is a memory passed down, something the old people saw once in their youth, an event more than a regular occurrence. The Sahara teaches that rain is not a given, that much of the planet's surface is rain-starved, waiting in perpetual patience for moisture that comes rarely, if at all. Bergen, Norway experiences rain 248 days per year. That's rain more than 2 days out of 3, making Bergen one of Europe's rainiest cities, a place where umbrellas are essential equipment and rain gear is everyday wear, not specialty clothing. The rain comes from Atlantic storms that blow in constantly, moisture from the ocean meeting the mountains behind the city and releasing precipitation with reliable frequency. Bergen's residents have a particular relationship with rain, a kind of resigned affection for it, proud of their city's wetness, making it part of their identity. The rain keeps the landscape green, feeds the many waterfalls in the surrounding mountains, fills the fjords. For Bergen, rain is not an interruption but a way of life, woven into the culture and expectations, the default weather around which everything else is planned. Sunshine is the surprise, the deviation, the weather that makes people comment and adjust their plans. The McMurdo Dry Valleys of Antarctica are among Earth's driest places, with some areas receiving almost no precipitation for thousands of years. These valleys are kept dry by katabatic winds, fierce downslope winds that sweep moisture away before it can precipitate, creating one of the most Mars-like environments on Earth. The valleys have exposed soil, rare in Antarctica, and what little snow does fall sublimates directly back to vapor without melting, maintaining the extreme aridity. The landscape is rocky, barren, almost lifeless, with only the hardiest microbes surviving in the harsh conditions. The valleys are used for research into extreme environments and as analogues for Martian conditions. They prove that even on a planet covered mostly by ocean, there are places where rain is nearly absent, where the water cycle barely touches. Cold, dry spots that seem to belong to a different world entirely, isolated from the moisture that sustains most life. Tropical rainforests receive between 79 and 394 inches of rain annually. It's enough rain to sustain the highest biodiversity on the planet, the most complex ecosystems, layered canopies and understories teeming with life that depends on that constant moisture. The rain falls in patterns, wet seasons and slightly less wet seasons rather than true dry seasons, and it comes often as afternoon thunderstorms, convective rain triggered by the heat building through the morning. Rainforest rain is warm rain, falling through warm air onto warm ground, and it's part of a tight cycle where the forest creates much of its own rain through transpiration. The sheer volume of water moving through a rainforest ecosystem, falling as rain, running in streams, evaporating from leaves, transpiring from roots, is staggering. The whole system a massive engine for cycling moisture, taking rain from the sky and sending much of it back as vapor to become rain again. The Mediterranean climate has distinct wet winters and dry summers. Rain falls when the westerlies shift southward in winter, bringing moisture from the Atlantic. But in summer, high pressure blocks those rain-bearing systems, creating months of dry weather. This pattern creates distinctive ecosystems adapted to the rhythm, plants that grow in the wet season and go dormant in summer, animals that time breeding and migration to match water availability. The Mediterranean climate is found in relatively few places worldwide: coastal California, central Chile, southwestern Australia, South Africa's Cape region, and of course the Mediterranean basin itself, all sharing this pattern of winter rain and summer drought. It's a climate that requires adaptation, that doesn't provide year-round water, that imposes a seasonal rhythm on everything. The rain, when it comes, is welcomed after the dry months, transforming landscapes from brown to green, filling cisterns and reservoirs, preparing the land for another cycle. Monsoon rains in Asia are caused by seasonal wind reversals. In summer, the land heats up more than the ocean, creating a low-pressure area that draws moist air inland from the sea. Air that rises and cools and releases its moisture as rain, often heavy rain, sustained rain that floods rivers and waters crops. In winter, the pattern reverses. Winds blow from land to sea, and the rains stop. Billions of people depend on monsoon rains for agriculture, for water supplies, for survival. And when the monsoon is late or weak, it can mean drought, crop failure, hardship. The monsoon is not just weather, but a fundamental structuring force for societies, cultures organized around its coming and going, calendars and festivals marking its phases. The monsoon rains are among the planet's most important precipitation patterns, moving water from ocean to land in quantities that sustain entire civilizations, a climatic gift and occasional curse that defines life across vast regions. England's reputation for rain is partly myth. London gets less rain than Paris. London averages about 23 inches of rain per year, while Paris gets closer to 25, and cities like New York receive over 40. What England does have is frequent drizzle and grey skies, rain that comes often but in small amounts, enough to require umbrellas but not enough to match the truly wet places of the world. The reputation for rain comes partly from the frequency rather than the intensity, the fact that you're likely to encounter rain on any given day, even if the total accumulation is modest. British culture has internalised rain as part of its identity, making it a topic of conversation, a shared experience, a reliable presence in daily life. But measured by total rainfall, England is moderate, not extreme, a place where rain is common enough to seem constant but not nearly as wet as the wettest places, a land of drizzle more than deluge. The Pacific Northwest's rain shadow effect creates deserts just miles from rainforests. Moist air from the Pacific rises over the Cascade Range, releasing its moisture on the western slopes in the form of the region's famous rains. But by the time it descends the eastern side, it's been wrung dry, creating semi-arid conditions in the same state that hosts temperate rainforests. The contrast is dramatic. Western Washington and Oregon are lush, green, perpetually damp, while eastern regions are dry, receiving a fraction of the rainfall, landscapes of sagebrush and irrigated farms rather than towering conifers and ferns. It's all due to the mountains forcing air to rise and cool on one side and descend and warm on the other, a process that creates two entirely different climates within 100 miles. Rain shadows exist wherever mountains block prevailing moisture, creating dry sides and wet sides, proving that rainfall is as much about geography as it is about climate. Some islands in the Caribbean receive dramatically different rainfall on opposite coasts. Trade winds blow consistently from the east, bringing moisture from the Atlantic, and this moisture falls on the windward, eastern sides of islands as orographic rain. By the time the air reaches the western, leeward sides, it's lost most of its moisture, creating drier conditions just a few miles away. A single island can have lush rainforest on one coast and scrubby dry forest or even cactus on the other, the rainfall difference creating entirely different ecosystems. Residents joke about living on the wet side or the dry side, planning their activities based on local rainfall patterns that can vary by tens of inches across just a few miles. It's a reminder that rain is local, that the island's topography matters as much as its latitude, that you can often find drier conditions just by driving west, crossing from the rainy side to the rain shadow. Clouds need tiny particles, called condensation nuclei, for water vapor to condense on. Without these particles, specks of dust, salt, smoke, bacteria, pollen, water vapor might remain vapor even when supersaturated, the molecules lacking a surface around which to organize themselves into droplets. The particles serve as gathering points, seeds around which moisture collects, enabling the formation of cloud droplets that eventually become rain. This is why clouds form more readily in some conditions than others, why air quality affects cloud formation, why even natural phenomena like forest fires or dust storms can influence rainfall by providing more condensation nuclei. Each particle becomes the heart of a cloud droplet and potentially the center of a raindrop, a tiny solid core around which water organizes itself, proof that even the purest seeming rain is a collaboration between vapor and particle, water and dust, sky and earth meeting to create precipitation. A cloud must contain about 1 million water droplets to form one raindrop. Each cloud droplet is tiny, barely 10 to 20 micrometers across, too small and light to fall, kept aloft by the slightest updrafts. But they bump into each other, merge, combine, and through millions of these combinations, a single raindrop gradually forms, growing to the size where it can overcome air resistance and begin falling. This process takes time, the droplet population slowly coalescing into drops, the many becoming few, the small becoming large. Inside a cloud, this is happening constantly, droplets colliding based on their different fall speeds and air currents, building up the population of drops heavy enough to fall as rain. 1,000,000 to 1, that's the ratio of cloud droplets to raindrop. A reminder that rain is an accumulation, a gathering, many small things patiently combining into something large enough to matter, to fall, to reach the ground. Supercooled water in clouds can remain liquid at temperatures below freezing. Water doesn't always freeze at 32 degrees Fahrenheit if it's pure and undisturbed, lacking a seed crystal or rough surface to trigger the phase change. In clouds, droplets can cool to well below freezing and still remain liquid, in a state of supercooling, balanced on the edge of becoming ice but not quite crossing that threshold. If a supercooled droplet touches an ice crystal or an aircraft or anything that provides a nucleation site, it can freeze instantly, the liquid becoming solid in a moment of release from its metastable state. Supercooled water is common in clouds between -10 and -20 degrees Celsius, existing in this between state, neither fully behaving like water should at that temperature nor yet transformed into ice, waiting for the right trigger to make the transition. The Bergeron process describes how ice crystals in clouds grow by stealing moisture from water droplets. Air that's saturated with respect to liquid water is actually supersaturated with respect to ice, meaning water molecules prefer to deposit onto ice rather than remain in liquid droplets. In a mixed-phase cloud containing both supercooled droplets and ice crystals, the ice crystals grow at the expense of the droplets, pulling moisture from them, getting larger while the droplets shrink and eventually evaporate. This process efficiently creates precipitation in colder clouds, the ice crystals growing large enough to fall, melting on the way down if they pass through warm air, arriving as rain even though they began as ice. The Bergeron process is named after the Swedish meteorologist who described it, and it's one of the primary mechanisms for generating rain in clouds where temperatures are below freezing, nature using ice as an intermediary to create liquid rain. Warm rain forms in tropical clouds without ice crystals involved. In warm clouds where temperatures never drop below freezing, rain forms purely through the collision and coalescence of water droplets, larger drops falling faster and catching smaller ones, merging with them, growing continuously as they fall. This process is efficient in tropical regions where clouds are deep and warm throughout, updrafts strong enough to keep drops suspended long enough for them to grow through collision. Warm rain can be intense, tropical downpours that dump inches in an hour, all formed without a single ice crystal, just liquid water at every stage. It's a different pathway to rain than the Bergeron process, simpler in a way, relying on nothing but droplets bumping into each other and sticking together, accumulation through collision, rain forming in the most straightforward way possible through simple liquid phase physics and the luck of encounters in a crowded cloud. Cloud seeding attempts to create rain by adding silver iodide to clouds. Silver iodide has a crystal structure similar to ice, and when particles of it are dispersed into supercooled clouds, they can serve as ice nuclei, providing surfaces for ice crystals to form where they might not otherwise. The theory is that these additional ice crystals will trigger the Bergeron process more effectively, leading to increased precipitation. Cloud seeding has been used for decades in attempts to increase rainfall or snow, to reduce hail, to clear fog, with mixed results. The effectiveness is hard to prove conclusively because weather is variable. Did it rain because of the seeding or because it was going to rain anyway? But in some conditions, particularly with supercooled clouds that lack natural ice nuclei, seeding does seem to increase precipitation somewhat. It's weather modification on a small scale, humans trying to tip the balance slightly in favor of rain, not creating weather from nothing but perhaps enhancing what's already there. Cumulonimbus clouds can tower 10 miles high and produce intense rainfall. These are the giants of the cloud world, thunderheads that build vertically through sheer force of convection, warm air shooting upward in powerful updrafts that can reach speeds of over 100 miles per hour inside the cloud. These updrafts carry moisture high into the atmosphere where it condenses and freezes, building massive ice crystals that eventually become too heavy for the updraft to hold, falling as rain, sometimes as hail. The rain from cumulonimbus clouds can be torrential, inches falling in minutes, overwhelming drainage systems, creating flash floods. These clouds have distinct life cycles, building, maturing, dissipating, their rainfall concentrated in the mature stage when the updrafts weaken and gravity finally wins, pulling all that accumulated moisture down at once. Cumulonimbus clouds are impressive and dangerous, beautiful and destructive, the atmosphere at its most energetic, building towers of ice and water that dwarf mountains and release their loads with sudden intensity. Nimbostratus clouds create steady, prolonged rain. Unlike the dramatic cumulonimbus, nimbostratus are flat, grey, widespread clouds that cover the sky like a ceiling and produce rain that can last for hours or days. The rain is typically moderate, steady, the kind that soaks into everything, that makes rivers rise slowly, that people wait out indoors with books and tea. Nimbostratus clouds form in stable atmospheric conditions, often associated with warm fronts, where gentle lifting of moist air creates widespread condensation. There's no violence in nimbostratus rain, no thunder or sudden downpours, just persistent precipitation that seems like it might never end. Grey skies releasing their moisture gradually, patiently, covering large areas with the same moderate rain. It's the rain of melancholy afternoons, of patience, of acceptance that today is a day for indoor activities, the clouds having settled in for a long visit with no apparent plans to leave soon. The collision coalescence process creates rain when droplets bump into each other. In a cloud, droplets of different sizes fall at different speeds, and this causes them to collide. When they touch, surface tension pulls them together into a single larger drop, which now falls a bit faster and has a better chance of catching even more drops. This is a runaway process. The bigger the drop gets, the faster it falls and the more drops it can catch, growing exponentially once it reaches a certain size. The process is most efficient in clouds with a wide range of droplet sizes and with strong updrafts to keep everything suspended and moving around. Collision coalescence is simple physics, just droplets bumping and sticking, but it's one of the fundamental ways rain forms, especially in warm clouds. the process that turns a cloud full of tiny droplets into precipitation large enough to reach the ground. Updrafts in clouds keep raindrops suspended until they grow heavy enough to fall. Inside a cloud, air is rising, sometimes gently, sometimes violently, and this upward-moving air can hold small drops aloft indefinitely. The drops are growing through collision and condensation, getting heavier, but as long as the updraft is strong enough, they stay suspended, circulating inside the cloud. Only when a drop grows large enough that its fall speed exceeds the updraft velocity can it escape and begin the journey to the ground. In particularly strong storms, drops can be lofted up and down multiple times, cycling through the cloud, growing larger each time, until finally they're heavy enough to overcome even the strongest updrafts. This is why intense storms produce larger raindrops. The drops have had more time suspended inside the cloud, more opportunities to grow before falling. The updraft is like a net catching small drops, releasing only those large enough to have earned their escape. Lightning in clouds helps create nitrogen compounds that rain brings to soil. Lightning's intense energy breaks nitrogen molecules in the air, allowing nitrogen to combine with oxygen to form nitrogen oxides, which dissolve in rainwater as weak nitric acid. When this rain falls, it brings nitrogen to the soil in a form plants can use, effectively fertilizing the ground. It's a natural nitrogen-fixing process, ancient and ongoing, part of how nutrients cycle through ecosystems. The nitrogen compounds in rain are dilute, but over time they add up, contributing significantly to soil fertility in areas with frequent thunderstorms. It's one of nature's ways of taking atmospheric nitrogen, which is abundant but unusable by most organisms, and converting it into biologically available forms. Lightning and rain working together, the storm not just bringing water but also nutrients, each flash contributing to the fertility of the soil below. A typical raindrop requires about 1 million cloud droplets to form. It's the same fact as earlier, but worth repeating because the scale is so striking. 1 million tiny droplets, each one invisible to the naked eye, all combining through countless collisions into a single raindrop that you can see fall, can feel on your skin. The cloud is a factory of these collisions, millions happening every second, billions of droplets gradually sorting themselves through mergers into the population of drops that will fall as rain. Each raindrop is a collective, 1 million individuals that found each other in the chaos of the cloud and decided, through physics rather than choice, to travel together. When you stand in rain, you're being touched by these collectives, each drop that hits you the result of 1 million small convergences, the many becoming one, over and over, throughout the cloud above. Clouds produce rain when their droplets reach about 0.02 inches in diameter. This is the threshold size, the point where a drop becomes heavy enough relative to its surface area that it can fall against the resistance of air, overcoming the forces that kept it suspended. Smaller drops remain in the cloud, larger drops begin to fall, and this size, about 0.5 millimeter, is where the transition happens. It's not a sharp boundary, and conditions like updraft strength matter, but generally drops smaller than this stay up and drops larger than this come down. This threshold exists because of how forces scale with size. Surface area increases with the square of radius, but volume increases with the cube. So as drops grow, their weight eventually overwhelms the air resistance their surface experiences. Physics determining when something tiny becomes something that falls, when cloud becomes rain. The temperature difference between cloud top and base affects rainfall intensity. A large temperature difference means strong instability, air at the bottom wanting to rise because it's warmer and less dense than air above, creating powerful updrafts that can build tall clouds and produce intense precipitation. A small temperature difference means weak instability, gentle lifting, less dramatic clouds, lighter rain. Meteorologists look at temperature profiles to forecast rainfall intensity, knowing that steep temperature gradients mean energy available for strong storms. The difference can be dramatic. The same amount of moisture in a stable atmosphere might produce drizzle, while in an unstable atmosphere it produces cloudbursts. Temperature difference is a measure of the atmosphere's potential, how much energy is available to convert moisture into precipitation, how eager the air is to move vertically and build clouds. It's one of the factors that determine whether a day brings sprinkles or downpours. Stratiform clouds produce gentle, widespread rain. These are horizontally layered clouds, stable and uniform, covering large areas with relatively uniform thickness. The rain from stratiform clouds is typically light to moderate, steady, lacking the intensity of convective storms, but often lasting longer and covering more territory. Stratiform rain is democratic rain, falling on everyone equally within the cloud's coverage, no hot spots or gaps, just widespread, gentle precipitation. This type of rain is ideal for soaking into soil rather than running off, for replenishing groundwater, for watering crops evenly. It's less dramatic than convective rain, less likely to make headlines, but it's the reliable rain that keeps rivers flowing and reservoirs filling. The rain that sustains agriculture and ecosystems through persistent, moderate delivery rather than occasional intense events. Stratiform clouds and their gentle rain are the workhorses of the water cycle in many regions, quiet and steady and essential. Rain erosion carves valleys and canyons over millions of years. Each raindrop that falls has mass and velocity, and when it hits soil or rock, it exerts a tiny force, dislodging microscopic particles. Multiply this by trillions of raindrops over millions of years, and you get the Grand Canyon, you get valleys and gorges, you get landscapes shaped fundamentally by the cumulative effect of water falling and flowing. Rain is gentle on human timescales, but relentless on geological ones, patient erosion that can cut through mountains if given enough time. The shape of continents, the pattern of rivers, the profiles of hillsides, all of this bears the signature of rain, water falling and flowing according to gravity, seeking the sea, carrying the land with it grain by grain, year by year. Rain doesn't just water the earth, it sculpts it, shapes it, writes its history into the contours of the ground. A heavy rainstorm can deposit 17 million tons of water on 1 square mile. That's the weight of 12 million cars, falling from the sky, absorbed by soil or flowing into streams, a staggering quantity of mass moved in a few hours. Just 1 inch of rain over a square mile equals about 17 million gallons, and heavy storms can drop many inches. This enormous mass transfer affects everything. It changes the weight load on the ground, affects soil stability, triggers landslides, floods rivers. The power of rain at this scale becomes obvious. The atmosphere capable of lifting and transporting and depositing quantities of water that dwarf human capacity to do the same. Each storm is a massive redistribution of mass, the sky giving back to Earth in bulk what evaporation took from it gradually, condensing days or weeks of evaporation into hours of precipitation, concentrating delivery in time and space. Rainwater percolating through soil filters out impurities naturally. As water moves through layers of soil, particles of clay and organic matter trap contaminants, bacteria and chemicals adhere to soil surfaces, and by the time the water reaches groundwater aquifers, it's often quite clean, naturally purified by its journey through Earth. This natural filtration is why groundwater is often cleaner than surface water, why wells can provide drinkable water without treatment. The soil acts as a massive filter system, billions of tiny passages and surfaces where water slows and interacts with minerals and microbes, emerging cleaner than it entered. Of course, this only works if the soil isn't already contaminated and if rainfall intensity allows for percolation rather than runoff. But where conditions are right, rain falling on soil begins a journey through one of nature's most effective purification systems, the earth cleaning water through simple contact and time. Rain returns nitrogen from the atmosphere to soil, fertilizing plants. Nitrogen makes up about 78% of the atmosphere, but in its gaseous form, most organisms can't use it. Lightning and certain bacteria can fix atmospheric nitrogen into compounds, and these compounds dissolve in rainwater as nitrates and nitrites. When this rain falls, it brings nitrogen to the soil where plant roots can absorb it, providing a key nutrient for growth. This process has been fertilizing the planet since long before humans invented agriculture, a continuous, gentle feeding of the soil from the sky. The nitrogen content in rainwater is small, but over time it matters, contributing to soil fertility in a way that's completely natural and sustainable. Rain is not just water, but a dilute fertilizer, each storm bringing trace nutrients that support the plants below, completing a cycle that moves nitrogen from air to soil to plants and back to air. The impact of raindrops helps disperse plant seeds across landscapes. Some plants have evolved seeds that stick to mud, and when raindrops hit muddy ground, they splash, throwing tiny particles including seeds into the air and moving them from their original location. Other seeds are designed to be carried by flowing rainwater, traveling down slopes in the runoff, colonizing new areas downstream. Raindrop splash can move seeds several inches per event, and over time this adds up, seeds migrating across a landscape through the accumulated effects of countless storms. It's a passive dispersal mechanism, the plant using rain's energy to move its offspring, requiring no wings or animal vectors, just the reliable fall and splash of water. Rain becomes a collaborator in plant reproduction, helping seeds find new ground, spreading species gradually across regions, the impact and flow of water serving the same function that wind or animals serve for other plants. Rain creates negative ions in the air that many people find calming. When water droplets break apart, as they do when rain hits surfaces or in waterfalls and fountains, they release negative ions into the air, molecules with an extra electron. Some research suggests these negative ions have mild effects on mood and well-being, possibly by increasing serotonin levels, though the evidence is mixed and effects are subtle. What's certain is that many people report feeling better, calmer, more relaxed in environments with higher negative ion concentrations, near rain, waterfalls, the ocean. It might be ions or it might be other factors like humidity, temperature, the sound of water, cultural associations. But the correlation between rain and a sense of calm is real for many people. Some chemical or psychological shift that happens when water falls and the air changes, becoming somehow fresher, cleaner, more breathable, more conducive to peace. Limestone caves form over millennia from slightly acidic rainwater dissolving rock. Rainwater absorbs carbon dioxide from the air and soil, forming weak carbonic acid. And when this slightly acidic water seeps through limestone, it dissolves the calcium carbonate, carving out passages and chambers over thousands or millions of years. The dissolved minerals sometimes precipitate again as stalactites and stalagmites, building structures as the water drips and evaporates, leaving behind what it carried in solution. Caves are sculptures of water and time, negative spaces carved by patient rain percolating through stone, following cracks, widening passages, creating underground worlds lit only when humans bring lights. Every cave is evidence of rain's power at geological timescales, proof that water given time can dissolve mountains, hollow out hills, create architecture from absence, all starting with slightly acidic rain soaking into the ground above. Rain triggers desert wildflower blooms in perfectly timed biological responses. Desert annual plants can lie dormant as seeds for years, waiting for rain, and they have chemical systems that prevent germination unless conditions are just right. Enough rain to support growth through completion of their life cycle. When the right rain comes, the desert explodes with color, flowers blooming in profusion, a brief, intense display of life that lasts only weeks before the plants die, leaving seeds for the next good rain. This timing is critical. Germinate too early or after insufficient rain and the plant dies before reproducing, wasting that iteration. So the seeds are selective, waiting for the signal that says conditions are favorable, and when rain provides that signal, the desert transforms, proving that even the driest places harbor latent life waiting for moisture to awaken it, rain the key that unlocks dormancy. Rivers are fed by ancient rainfall stored in underground aquifers. The water flowing in rivers often fell as rain months, years, even centuries ago percolated into the ground, traveled slowly through rock formations and emerged as springs that feed streams and rivers. During dry periods when no rain falls, rivers keep flowing because of this stored water, ancient rain making its way slowly back to the surface. Some aquifers are thousands of years old, fossil water from wetter climates, and when we pump them faster than rain can recharge them, we're mining history, using up ancient rainfall that won't be replaced in human timescales. Rivers connect present rain with past rain, surface water with groundwater, the water cycle operating across timescales from days to millennia, rain from different eras mixing in the same stream bed, past and present flowing together toward the sea. Rain on hot pavement releases trapped air pollutants back into the atmosphere. Ozone, nitrogen oxides, and various organic compounds settle on surfaces, and when rain falls on them, especially the first rain after a dry spell, it can volatilize these compounds, sending them back into the air in a brief spike of pollution. This is one reason the air can smell oddly chemical during the first rain after a long dry period, the accumulated deposits being redistributed. It's a reminder that rain doesn't just clean the air, it also interacts with whatever's already there. And in polluted environments, that interaction can briefly worsen air quality before the continued rain eventually washes things away. Rain and pollution have a complex relationship, rain initially disturbing deposits before eventually removing them. The first rain the dirtiest, later rain progressively cleaner as surfaces are washed. The storm, a multi-phase process of mobilization and removal. Wetlands act as natural sponges, absorbing and slowly releasing rainwater. When rain falls on wetlands, the water doesn't immediately run off, but soaks into the saturated soils and pools in shallow basins, stored temporarily before gradually releasing into streams or percolating to groundwater. This natural storage reduces flooding downstream by holding water during storms and releasing it slowly later, extending the benefits of rain over time. Wetlands also filter the water as it passes through, removing pollutants and sediments, providing habitat for countless species and supporting biodiversity. But wetlands have been drained and filled across much of the world, eliminating this natural rain management system, leading to more severe flooding and less water storage. The relationship between rain and wetlands is symbiotic. Rain sustains wetlands, wetlands manage rain, and both suffer when the connection is broken by human development. Rain runoff carries nutrients from land into oceans, feeding marine life. When rain falls on land, it picks up nitrogen, phosphorus, organic matter, and other nutrients as it flows toward the sea. These nutrients, which might otherwise be trapped in soil, are transported to coastal waters where they support plankton blooms, which feed fish, which feed larger predators, the entire marine food web benefiting from nutrients delivered by rain. Of course, runoff can also carry pollutants, fertilizers, pesticides, industrial waste, which can cause harmful algae blooms and dead zones. But in natural systems, rain-delivered nutrients are essential for ocean productivity. One of the ways the water cycle connects terrestrial and marine ecosystems, moving not just water but the elements necessary for life, stitching together land and sea through the medium of falling and flowing water, rain the messenger carrying Earth's bounty to the ocean. The pattern of rainfall shapes entire ecosystems and determines which species thrive. Rainforests exist where rain is frequent and abundant, grasslands where it's moderate, deserts where it's rare. But it's not just the amount, but also the timing. Monsoon regions get all their rain in a few months, Mediterranean climates get rain in winter but not summer, and these patterns select for different survival strategies. Animals and plants have evolved to match their life cycles to local rainfall patterns, breeding when water is available, going dormant when it's not, migrating to follow the rain. Change the rainfall pattern, and you change the ecosystem, species that were successful becoming struggling, new species moving in. Climate change is shifting rainfall patterns globally, moving rain from places that used to be wet to places that used to be dry, and ecosystems are struggling to adapt. The ancient partnership between life and local rain patterns breaking down faster than evolution can adjust. Rain saturates soil, preventing wildfires from spreading. Wet soil, wet vegetation, wet leaf litter, none of these burn well. Rain is the most effective fire prevention, soaking fuel loads and raising humidity, making it difficult for fires to start or spread. Fire season typically comes at the end of long dry periods, when rain has been absent for months, and fire season ends when the rains return, transforming the landscape from dry and flammable to damp and resistant. In fire-adapted ecosystems, this cycle is natural, fire and rain taking turns shaping the landscape. But in many places, human fire suppression has disrupted these cycles, and changing rainfall patterns mean longer dry seasons, more severe fire seasons. Rain and fire are opposites, wet and dry, growth and destruction, and the balance between them determines the character of entire regions, whether they burn regularly or rarely, whether they're lush or stark. Flash floods can occur when just 6 inches of rain falls in a few hours. 6 inches is not particularly remarkable as a total, but concentrated in a short time, it can be devastating. The ground can't absorb water that fast, so it runs off, collecting in drainages that quickly become raging torrents. 6 inches of flowing water can knock you off your feet, 12 inches can sweep away cars, and when heavy rain concentrates in a small area, the runoff concentrates too, creating walls of water that rush down normally dry washes or small streams, catching people by surprise. Flash floods are among the deadliest weather phenomena because they develop quickly and can occur in places far from where the rain fell, water gathering from a large area and concentrating in one channel. It's a reminder that rainfall intensity matters as much as total amount, that rain falling too fast is as problematic as rain not falling at all. Some frogs remain dormant underground for years, waiting for rain. Desert-dwelling species like spadefoot toads burrow deep into the soil and enter a state of torpor, their metabolism slowing dramatically, cocooned in a layer of shed skin that reduces water loss. They can wait years like this, not dead, but not quite alive, suspended between states, until finally rain soaks into the ground and wakes them. They emerge, breed frantically in temporary pools, their tadpoles developing in days or weeks, the whole life cycle compressed into the brief window of moisture. Then they burrow again, waiting for the next rain, however long that takes. These frogs are adapted to rain as the trigger for activity, their entire existence organized around infrequent precipitation events, proof that life can persist in places where rain is rare by becoming patient, by waiting as long as necessary for water to return. Desert toads can absorb rainwater through their skin in minutes. Their skin is permeable, designed to take up water rapidly when it's available, rehydrating their bodies after long periods of dormancy. When rain comes, toads that were buried in dry soil can absorb enough moisture through their skin to restore normal body functions within minutes, a rapid rehydration that allows them to emerge and breed while pools last. This adaptation is essential in environments where water is fleeting, where any delay means missing the opportunity. The toad's skin is not just a barrier but a tool, actively pulling water in when it's present, making the most of rain while it lasts. It's a beautiful adaptation, the body designed to drink rain directly, to take advantage of precipitation with maximum efficiency, not wasting time, responsive to water the moment it arrives. Spadefoot toad tadpoles must complete their entire development in temporary rain puddles. These puddles exist only for days or weeks after rain, then dry up completely, so the tadpoles have to develop from egg to metamorphosed toadlet in that narrow window. They grow faster than most amphibians, their development compressed, eating voraciously, racing against evaporation. If the puddle dries before they can metamorphose, they die, so their development is calibrated to typical puddle lifespans in their habitat. Some spadefoot species have two forms of tadpoles, omnivores and carnivores, with the carnivores growing faster by eating other tadpoles if necessary, a harsh adaptation to the pressure of temporary water. It's life on a deadline, development driven by the knowledge that time is limited, the rain puddle a ticking clock counting down to desiccation, the tadpoles rushing through stages that other species take months to complete. Rain triggers synchronized breeding in many tropical amphibians. When the first heavy rains of the wet season arrive, frogs and toads gather at breeding sites, sometimes thousands of them, calling and mating in a brief, intense reproductive burst. The rain is the signal that triggers this gathering, telling the amphibians that conditions are right, that water is present for eggs and tadpoles. The synchrony has advantages: overwhelming predators with sheer numbers, ensuring that everyone finds mates, concentrating reproductive effort when success is most likely. The chorus of calling males during these events can be deafening, the night full of sound, the whole amphibian population responding to rain in unison. It's one of the ways rain shapes animal behavior, becoming a trigger for life events, the presence of moisture determining when species breed, migrate, emerge from dormancy. Rain not just a physical phenomenon but a biological signal that organisms have learned to read and respond to. Some plants have evolved leaves that channel rain directly to their roots. Bromeliads and other epiphytic plants have leaves arranged in rosettes that capture and funnel rainwater to their centers, where roots can absorb it. Some terrestrial plants have leaves that slope inward, directing rain down the stem to the base of the plant where roots are concentrated. This adaptation makes rain more useful, ensuring that water doesn't just fall on leaves and evaporate but is guided to where it can be absorbed. In environments where rain is infrequent, channeling every drop to roots makes the difference between surviving and dying. The leaf architecture is shaped by rain, designed to work with it, to make the most of each precipitation event. Plants that can capture and direct rain have an advantage over plants that just let it fall where it may, their form-following function, the shape of leaves reflecting the importance of water management. Rainforest canopy trees can intercept 90% of rainfall before it reaches the ground. The dense canopy acts as a barrier, leaves and branches catching rain, some of it evaporating from leaf surfaces, some dripping gradually through the canopy, some flowing down trunks. Only a small fraction reaches the ground directly as throughfall, the rest taking a longer path through the vertical structure of the forest. This interception has major effects. It reduces erosion by slowing water's descent, provides moisture for epiphytes living in the canopy, cools the forest through evaporation. The ground beneath a rainforest receives more mist than rain, gentle dripping rather than direct downpour, the canopy mediating the rain, softening its impact, redistributing it in time and space. The trees don't just grow in rain but actively manage it, their structure shaping how precipitation reaches the soil, the forest and rain in constant interaction. Earthworms surface during rain not to avoid drowning but because they can travel easier. Worms breathe through their skin and they need it moist so they can actually survive submerged for days. But they move slowly through soil, and when rain saturates the ground, they can move more quickly across the surface, covering more distance to find new feeding areas or mates. The moisture of rain makes the air humid enough that their skin won't dry out, allowing them to take advantage of this brief opportunity for faster travel. So the worms on sidewalks after rain aren't fleeing their burrows but exploring, taking advantage of conditions that allow movement without the usual risk of desiccation. Some get stranded when the sun comes out and surfaces dry, but many make it to new areas, the rain providing a window for migration. It's not distress but opportunity, worms reading rain as a signal for travel, for expanding their range. Some species of ants build elaborate drainage systems around their nests. Leafcutter ant colonies, which can house millions of individuals, construct mounds with channels designed to divert rainwater away from the nest interior, preventing flooding. The mound itself is shaped to shed water, and interior tunnels slope to keep water from pooling. These drainage systems are sophisticated, protecting the fungus gardens the ants cultivate, maintaining dry conditions in the nest even during heavy rain. The ants are constantly maintaining and adjusting their drainage, responding to rain events by repairing damage, extending channels, improving the system. It's engineering, infrastructure built specifically to manage rain, ants treating water as a problem to solve through construction, their nests designed with hydrology in mind, proof that many species don't just endure rain but actively protect themselves from it through structures and behaviors evolved over millions of years. Migrating birds time their journeys to follow seasonal rainfall patterns. Many species move between regions following the availability of food, which is itself linked to rain. Insects boom after rains, plants green up and produce seeds, water sources fill. By following rainfall patterns, birds ensure they arrive at stopover sites and destinations when food is abundant. Some species breed in temperate regions during summer when rain sustains food supplies, then migrate to tropical regions timed to arrive with the rainy season there. The birds are following rain across the landscape, their migration routes and timing shaped over generations to match where and when rain creates favorable conditions. When rainfall patterns shift due to climate change, these timed migrations can become mismatched, birds arriving too early or too late for the food pulses they depend on, ancient patterns disrupted by rain falling at different times or in different places. Salmon populations depend on rainfall to maintain river flow for spawning. Salmon swim upstream to breed, and they need adequate water flow to navigate, to reach spawning grounds, to survive the journey. Low rainfall means low river flows, which can block migrations, strand fish, reduce spawning success. The salmon life cycle is timed to coincide with seasonal flow patterns maintained by rain and snowmelt, generations adapting to the reliable delivery of water at certain times of year. But droughts and changing rainfall patterns can disrupt this, rivers running low when salmon need them high, migrations failing, populations declining. Salmon and rain are connected across landscapes, the fish depending on precipitation falling in distant mountains to create the flow conditions they need to reproduce, a connection that spans hundreds of miles, fresh rain in the headwaters affecting ocean. Going fish weeks later when they return to spawn in the flows that rain created. The sound of rain activates the brain's relaxation response, lowering cortisol. Research shows that natural sounds, especially the white noise-like qualities of rainfall, can reduce stress hormones and promote relaxation. The sound is consistent but not monotonous, variable but not unpredictable, hitting a sweet spot that brains find soothing. Recordings of rain are used in meditation apps and sleep aids because they're so reliably calming for most people. This might be evolutionary. Rain meant safety for our ancestors, shelter from predators, water availability, a sound associated with survival rather than threat. Or it might be acoustic properties, the frequency spectrum of rain matching something our auditory systems process as non-threatening. Whatever the mechanism, rain sounds calm people, and listening to rain, real or recorded, activates parasympathetic nervous systems, slowing heart rates, deepening breathing, creating physiological relaxation that mirrors psychological calm. Humans can smell approaching rain through petrichor from up to several miles away. Our noses are extraordinarily sensitive to geosmin, detecting it at concentrations as low as 5 parts per trillion, making it one of the most detectable compounds for humans. When rain first hits dry ground, even several miles away, released geosmin molecules can travel on winds, arriving before the rain itself, giving us advance warning. This sensitivity likely evolved because for our ancestors, smelling rain meant finding water sources, a survival advantage in savanna environments where water was scarce. The ability persists even though most modern humans don't need it for survival. Our nose is still tuned to detect that distinctive earthy scent, still responding to it with recognition, still knowing without being taught that this smell means rain, means water, means change in the weather coming soon. Rain increases negative ions in the air, which studies link to improved mood. When water molecules break apart through splashing or mist formation, they can release negative ions, oxygen molecules that have gained an extra electron. Some research suggests these negative ions affect serotonin production in the brain, potentially improving mood, though the effects are subtle and not everyone agrees on the mechanisms or significance. What's documented is that many people report feeling better in environments with higher negative ion concentrations, and rain consistently increases negative ions in the air. Whether this is direct neurochemical effect or the combination of many factors, humidity, temperature, sound, smell, psychological associations, the correlation between rain and improved mood is real for many individuals. Rain bringing not just water but a shift in both air quality and human experience. Subtle chemical changes that affect consciousness in ways we're still working to understand fully. Ancient civilizations built entire cities around capturing and storing rainwater. In regions with seasonal rain and no permanent rivers, rainwater harvesting was essential, and cultures developed sophisticated systems, cisterns, reservoirs, channels, to capture and store rain for dry months. The Nabateans built Petra with advanced water systems that captured flash flood runoff and stored it in rock-hewn cisterns. The Maya built reservoirs at Tikal that held millions of gallons of rainwater. These weren't small-scale projects, but city-defining infrastructure, entire settlement patterns determined by the ability to collect and store rain, architecture shaped by the need to catch every drop that fell. When these systems failed due to drought or damage, cities could collapse, their populations unable to survive without their stored rain. These ancient systems show that humans have long understood rain's value and variability, building complex infrastructure to buffer against its unpredictability. Civilizations rising and falling based partly on their success in managing captured rainwater. The Inca Empire used sophisticated terrace systems to manage mountain rainfall. In the steep terrain of the Andes, rain runoff could cause severe erosion, but the Incas built extensive terracing that slowed water's descent, allowed it to soak into soil, prevented erosion, and created microclimates that extended growing seasons. These terraces, thousands of them across the empire, were engineering marvels designed to work with rain rather than fight it, turning potential destruction into agricultural productivity. The terraces captured rain, distributed it evenly across slopes, prevented flooding in valleys below. Even today, many Inca terraces are still functional, still managing rainwater as they did 500 years ago, testimony to how well they understood water's behavior on slopes, how rain needed to be slowed and spread and absorbed rather than allowed to rush downhill unchecked. Rain shaped Inca agriculture, And Inca engineering shaped how rain affected the landscape, a partnership between human ingenuity and natural precipitation patterns. Traditional rain harvesting in Rajasthan, India sustained communities for millennia. In this desert region, communities built step wells, tanks, and elaborate systems to capture and store monsoon rain, making it through 8 dry months on the 4 months of rain they received. Every village had systems scaled to its needs, communally maintained, essential for survival. These systems were often architectural as well as functional, beautiful structures that showed how important rain was to the culture, its capture celebrated and enshrined in elaborate construction. With modern infrastructure like piped water, many traditional systems fell into disrepair and communities became dependent on distant sources. But recent droughts and water scarcity have led to revival of traditional rain harvesting. Recognition that capturing local rain is more sustainable than pumping groundwater or transporting water long distances. The old systems worked because they were adapted to local rainfall patterns, sized appropriately, maintained communally, treating every monsoon as the gift it was, every drop too precious to waste. A 1-inch rainfall on an acre of land equals 27,154 gallons of water. That's enough to fill a small swimming pool, and it falls from the sky in a few hours, every acre receiving this gift, free water delivered wherever clouds form. Scale this up to a square mile and a 1-inch rain deposits about 17.4 million gallons, an enormous quantity made invisible by being spread across large areas. But when you calculate the volume, the mass, the energy required to lift that water into the air and the energy it releases falling back down, you begin to appreciate rain's magnitude. Each modest rainstorm moves quantities of water that would require fleets of trucks to transport, nature accomplishing massive redistribution of mass casually, routinely, without fanfare. Understanding these numbers helps explain rain's power to flood, to erode, to sustain, to shape. So much water falling from such height, physics and chemistry combining to move oceans through the sky. Modern cities lose 95% of rainwater to runoff instead of absorption. Pavement, roofs, compacted soil. These impervious surfaces prevent rain from soaking into the ground, so it runs off into storm drains and rivers carrying pollutants with it, causing flooding downstream, wasting an opportunity to recharge groundwater. Before development, that same landscape might have absorbed 80% or more of the rain, slowly filtering it into aquifers. But urbanization flips this ratio, making cities into slick surfaces that shed rain rather than absorb it, losing the resource even as they complain about water scarcity. The solution involves green infrastructure, permeable pavements, rain gardens, bioswales, green roofs, all designed to slow and infiltrate rain where it falls rather than rushing it off-site. Cities built without consideration for rain management turn precipitation into a problem rather than an asset, losing the benefits of natural infiltration and storage that would occur if the land could absorb what falls. Rain gardens in urban areas can reduce flooding by 30 to 40%. These shallow planted depressions are designed to capture runoff from impervious surfaces, holding it temporarily while it slowly infiltrates into the ground, instead of running directly into storm drains. A rain garden can absorb large quantities of water, reducing peak flows during storms, filtering pollutants, recharging groundwater. They're relatively simple to install and maintain, requiring just a depression planted with native species adapted to both flooding and drought. The effect scales. One rain garden helps a little. Thousands of them across a city can significantly reduce flooding problems, demonstrating that working with rain through distributed small-scale solutions can be more effective than massive centralized infrastructure. Rain gardens represent a shift in thinking, from moving water away as fast as possible to keeping it where it falls, managing rain through infiltration rather than conveyance, treating it as a resource to capture rather than a nuisance to dispose of. The rhythm of rainfall has inspired music and poetry in every human culture throughout history. From ancient rain songs meant to summon precipitation to contemporary compositions that capture rain's patterns, humans have found in rainfall a source of artistic inspiration. The rhythms are natural, but varied enough to be interesting, the sound textured, the visual patterns hypnotic. Rain appears in creation myths, love poems, dirges, celebration songs, every genre and tradition finding something in falling water worth honoring in art. Perhaps it's rain's essential nature, we need it, notice it, feel it personally, that makes it so present in human creativity. Or perhaps rain's patterns really do echo something musical, rhythms that our pattern-seeking brains recognize and want to replicate, extend, play with. Whatever the reason, rain and art are old companions, falling water inspiring humans to create patterns in sound and word that mirror or counterpoint the patterns of droplets falling, cultures across the world independently deciding that rain deserves to be sung about, written about, remembered in verse and melody. And so we arrive at the end of our journey through rain, through these 100 small truths about water falling from sky to earth. You've travelled from the shape of drops to the wettest places on the planet, from the chemistry of petrichor to the civilizations built on captured rainwater. Each fact a step deeper into understanding this most familiar and most essential weather. Rain has been falling since long before we were here to see it, and it will keep falling long after, patient and persistent, the atmosphere's way of returning borrowed water to the ground, completing cycles that connect ocean to cloud to earth to ocean again. Rest now, let these facts settle like rain soaking into soil, and know that somewhere on this planet, right now, rain is falling, drops tracing their ancient paths from cloud to ground, carrying out their small essential work of watering the world. Sleep well.